Hello everyone, thanks for attending the special issue about future electricity network infrastructures. It's my honor to make a presentation today. My name is Yachen Tang and I'm from Envision Digital Company. My topic is electricity carbon graph modeling and analysis. Nowadays, the carbon emissions of the energy industry account for 88% of China's total carbon dioxide emissions, which the carbon emissions of the power industry occupies around 40% of the total emissions in the entire energy industry, and the goal of carbon neutrality and carbon peaking. The power industry needs to play an essential role in carbon emission reduction. It is urgent to carry out the electricity carbon correlation analysis and research the mechanism of carbon intensity calculation that reflects the green attributes in electricity. In terms of carbon flow tracking and traceability, the carbon intensity calculation process does not consider the transmission of electricity energy in the power grid. It is necessary to consider the physical transmission paths in the grid, realize the online tracking of carbon flow between power plants, substations, and users, and analyze the transmission law of carbon flow in the power grid online. The main contribution of this paper is to introduce an approach of modeling grid spatio-temporal data in graph database and electricity carbon correlation analysis to construct the one graph of electricity carbon system. The framework of the system is shown in the figure, which consists of several modules: index generation, retrieval system, result optimization, and result display. This scheme is generally carried out in three levels: data collection, conversion of relational data to graph data, and the construction of the one graph of electricity carbon system. The data collection is first performed. The data covers power generation, transmission, transformation, distribution, and consumption. It can be collected through existing independent information systems, such as power grid scheduling, network topology, and measurement data provided by the dispatch system, equipment ledger data supplied by the produce management system, distribution network topology and measurement data provided by the distribution automation system, and so on. After the data is collected through the data platform, it supports multi-source relational data structure analysis. According to the analysis results, the corresponding nodes and the relationship between the nodes are defined in the graph database to generate a graph schema that meets the requirements of the electricity carbon correlation analysis. Since the data provided by different information systems are redundant, load all the data into the graph database according to the built graph schema, and then perform graph similarity analysis for each data node to achieve data deduplication and fusion. This process is actually a process of transformation from relational data to graph data, which eventually forms the one graph database. Combining the electricity carbon correlation analysis algorithm and the visualization display strategy, the system is finally constructed. Electricity carbon intensity is defined as the carbon dioxide content per kilowatt-hour of electricity in a given area during a unit of time. The basic calculation methods of electricity carbon intensity consist of three parts. One is the calculation of thermal power carbon emissions on the power generation side. Two, the carbon intensity in grid sites can be calculated according to the regional power intensity. And three, the carbon intensity on the user side can be calculated by multiplying the region carbon intensity and electricity consumption to obtain the carbon emissions of users. The direct emissions from electricity generation in the region can be defined as equation 1, in which WJCO2T is the direct carbon dioxide emissions from the power system in area J in the T period. GENIT is the power generation amount of the I power supply points in the T period within the area J, and EFCO2IT represents the carbon intensity of I power generation at time period T. The carbon emissions from electricity loads in the region can be defined as equation 2, where CLJCO2T is the carbon emissions of loads from the power system in area J in the T period. GENJT is the sum of power generation in the T period within the area G, and the load JT represents the sum of loads or power consumption at time period T in area G. As an example shown in the figure, the electricity carbon intensity in the area 1 can be calculated through the power generation methods as P1 times carbon emission benchmark value of thermal power plus P4 times electricity carbon intensity of area 2 divide P1 plus P2 plus P3 plus P4. Well, it can be calculated via the power consumption method as P1 times carbon emission benchmark value of thermal power plus P4 times the electricity carbon intensity of area 2 divide P5 plus P6 plus power loss. The carbon intensity on the user side equals carbon intensity of area 1 times P6. Schema is used to describe a collection of objects in a database. When constructing a graph database schema, the graph database nodes can be regarded as data ontology. The attributes in nodes can be considered as ontology attributes, and the associations between nodes can be regarded as edges. The schema generation process is shown in the first figure. For the multi-source relational data structure analysis part, this process analyzes the data table structure and distinguishes primary key nodes, foreign key nodes, and feature attributes to build an initial candidate node set. We then define feature attributes as node attributes in the corresponding primary and foreign key nodes. In the node clustering part, we implement candidate node clustering through the string similarity of candidate node names. In the node determination part, in each clustered node graph, the node name of the cluster graph is determined according to the word frequency statistics. Then we perform associate nodes according to the connection relationship between primary and foreign keys. We use edges to associate nodes to perform a schema that meets the requirements of one graph of electricity carbon. In the data fusion based on node attributes graph part, we load the multi-source data based on the schema, define each node and attribute as a different vertex, and connect the associated vertices in the schema with their attribute vertices to form a node attribute graph. We then determine whether the associated attribute of the vertex is a shared attribute node, and count whether the number of shared attribute nodes of different vertices is greater than the preset threshold. Finally, we retain the first loaded vertex data and fuse redundant data as one vertex. As an example shown in the second figure, suppose the equipment-related attributes in the schema include manufacturer, voltage level, belonging substation, equipment name, model, and so on. After loading data, we found that the manufacturer, voltage, substation, and model vertices of device 1 and device 2 are the same, which means they can be shared. Therefore, we determined the device 1 and device 2 are the same devices. we retain the first loaded relevant information of device 1, fill the attributes not included in device 1 but contained in device 2 into the vertex of device 1, and eliminate device 2 to realize data fusion. In the case study part, we randomly selected 10 tables from the information system of the power dispatch system, the produce and management system, and the distribution automation system, and check whether the primary and the foreign key information of each table has a corresponding node in the schema. Check whether the table attributes of all tables are reflected in the schema in the form of nodes or attributes. We then randomly extract 10 pieces of data from each table, check whether each piece of data and its associated information are mapped to the graph database, and can form a complete node attributes graph. Table 1 shows the test results of the conversion from multi-source relational data to the graph data. According to the validation results, it can be seen that the parsing of the relational data table and the mapping accuracy of the graph schema can reach 100%. The node mapping accuracy of the data can reach 100%, and the number of associated nodes in the attribute graph of each mapped node is slightly less than the number of associated data in original data tables. The reason for the inspection is that redundant attributes has been removed by data fusion. For the computational speed and correctness of electricity carbon intensity, we verify the calculation results of electricity carbon through the selected area in the second figure. Each city in the figure is a node. We assume each node is an area, where nodes A, E, G are power generation nodes, in which A is hydropower, E and G are thermal power. H is an equivalent virtual station, and the default carbon intensity value is 108. We use the power generation method to calculate the carbon intensity of each region, and use the results of the power flow calculation to calculate the regional carbon emissions. Table 2 shows the test results of electricity carbon analysis. According to the grid topology and power direction, it can be found that the carbon intensity and carbon emissions of regions that use large amounts of thermal power are higher than those that mainly use hydropower. Although the calculation results of carbon intensity in some areas have slightly deviated, the accuracy of the overall analysis results is higher than 99%. The reason for the deviation is the setting of the convergence threshold during calculation. The overall calculation time is around 600 ms. The proposed work is to use graph database and graph computing technology to build a graph model to realize the fusion of electricity and carbon spatial temporal data in one graph database, and integrate electricity carbon correlation analysis to discover the calculation of electricity carbon intensity and emissions in a target area according to the power flow calculation period. The constructed system can provide data support for modern electricity carbon management and energy conservation and emission reduction in power system. Thank you very much for your listening. If you have any questions, please feel free to contact me. Thank you again.